My name is Jamie Butler, and today I'm going to be speaking on DCOM. DCOM is going to be talking about kernel object manipulation and not in the sense of the DCOM that Microsoft has. I work at a company called HB Gary. We're a small consulting firm, and where I started this work was doing contributions to the Rootkit site on Rootkit.com, which Greg Hoagland runs, and that's how I got into this. So I'm going to preface the talk with explaining that direct kernel object manipulation runs in the kernel, so it requires that a rootkit of some sort is installed. I'm not going to speak about how you gain privileges to install a rootkit. Other talks here have discussed those issues, such as using buffer overflows, using heap overflows. Dave Attell, David Litchfield, and so on and so forth are much better at that than I am, so I'll keep to the kernel, and I'll assume that there's somebody else that can get me access. And this also can be done through, you can install drivers through some social engineering, through email attachments, different things like that. And certain users have ability to install device drivers, at least in the limited sense of the fashion. Maybe you're a large corporation and you allow certain users to be able to install their own printer drivers and so forth. So we won't talk about how you get the rootkit installed, but we'll cover what it can do once it gets there. This talk is mainly focused on the offensive aspects of rootkits and rootkit technology. I did work for an intrusion prevention company or an IDS company. So at any point, if you see this as a great problem, you have questions about how to solve it, the slides, although some of them address it a little bit, the preventative measures, I do encourage you to ask, and we can have a dialogue in the class that way, or in the speech. So, we'll start off with a few slides about operating systems and how they work. This isn't a Windows-specific talk, although I concentrate in Windows because that's where all my experience mostly lies. I also will show you some slides of how this is completely possible to do in Linux, and it's possible to do in other operating systems. So this isn't an attack against any one particular vendor. First of all, we're all familiar, probably most of us are familiar with the Win32 API. That's what programs use to request functionality of the kernel of the operating system. You can use the Win32 API to create sockets, to open, to send data, to list processes, to list drivers. Task Manager and other applications rely upon these APIs. So it's a well-known interface into the operating system. Your process will link in kernel32.dll. Kernel32.dll uses ntdll, and that's all in the userland portion of the process. Once ntdll and kernel32 do their work, then the kernel itself is requested to do the function, and then now we're down in kernel mode. So we're in the low levels of the kernel, and this is where the protected memory is. So these are where our, I call them objects, are stored. Microsoft usually refers to them as objects, but this is an object is in a C++ class. These aren't methods and data that operate upon, or methods that operate upon the data. All these are is basically structures. And these structures are used for accounting purposes, again, to list open ports, to list processes, things like that. And also for tokens you see there, because tokens describe what a process is allowed to do, what privileges it has. So in the Intel architecture, you can read the Intel architecture manuals. There's 3 of them for the x86. There's 4 rings described. Anything that I said was kernel mode is at ring 0. and anything that I say is user land or user mode is at ring 3. So you could have, Intel, although it provides these other 2 rings, no one usually uses those rings. And that's where the problem lies. So we have an operating system. It's provided by the vendor. And we have third-party applications which are provided by different sets of vendors. And then we also have different hardware and the hardware comes with device drivers. Device drivers are in the kernel, they're in ring 0, and because in this particular case the vendor, being Microsoft, cannot write HP's printer driver because HP wants to keep that to itself, the kernel has to load third-party vendors' drivers into the kernel. And once you're there, there's no separation of powers. So if you understand the kernel well enough, your printer driver can take over these objects and just stomp on memory. If it understands how the kernel is using the objects, you can do this in a fairly reliable fashion without blue screening the box, which is what I'll show you. So consumers are starting to demand more. We've noticed there's a huge explosion almost, it seems like these days, in host-based intrusion prevention systems, in antivirus software, in personal firewalls, and all these different pieces are coming together into one software solution. So the host-based intrusion prevention systems, they're in your kernel, they're hooking system calls, they're looking for bad behavior. Personal firewalls, doing much the same. They're layering in the network device architecture. All these products are coming into one cohesive unit and sold by a particular vendor. So even your antivirus software now is hooking your kernel to look at registry keys. So I know for a fact like Symantec and some others do that. These are all to provide the user with more protection that maybe they don't get by default from the kernel itself. So HIDS, HIPS, I'm not sure if everyone's familiar with those terms. HIDS in this case is host-based IDS, and HIPS is host-based intrusion prevention systems. So to augment the kernel and to provide an additional layer of security, they try to detect processes. So you could set up your HIPS product to say, well, my corporate policy is never run Internet Explorer because it has ActiveX, it has all these other things that our security people just don't want to be able to have to manage. So we'll only run, Mozilla. So you could have a HIPS product that when it sees IE Explorer.exe try to get ran, it just says no. And you can do that by hooking the kernel and different things like that. It also looks for files, see what was changed on the file system. We're all familiar with Tripwire. It was probably one of the first to do this. The personal firewall paradigm is looking at connections made to other boxes. So you can say, okay, well, I want to allow my users to be able to surf the web, but I never want to see someone FTPing back into their box on port 23. So your intrusion prevention system, your personal firewall, whatever you want to call it today, could say, well, never let inbound connections, and so on and so forth. We're all familiar with this. The problem lies in the fact that still the heart of the reporting mechanism is the operating system itself. And because the third-party vendors haven't taken the time, or not so much that, it's fairly, in a commercial setting, you don't want to start querying the objects yourself because that's dangerous. And as new service packs and so forth come out, it isn't going to be consistent how these things are used and where they are. So you can't just sort of hard code it yourself. You have to ask the operating system for help. That's how it was designed. That's what it's there for. So that's one point of failure. If the kernel's subverted, then all bets are off. And the reason the kernel can be subverted is because there's no separation of power between its own memory, i.e. objects, and those of third-party drivers. So within a kernel, how is HIDS and HIPS possible? I'll argue that rootkit technology is dual use. The fact is, you can install a rootkit to hide things, or it's just basically semantics that your HIPS and HIDS are really rootkits. They're doing hooking, they're doing all these other things, they're just not doing it for a malicious purpose. So they can query the kernel reporting functions directly, such as if your HIPS product wants to know all the device drivers loaded on the system, it can call ZW query system information, pass it a parameter saying, I'm asking for drivers, and the kernel will gladly report back to the product, here's all the drivers that are loaded. Another way to accomplish HIPS and HIDS functionality is you can hook the user land APIs. And there are a lot of products that do this now. And the reason you may want to do this is just some things are easier to do at the user land level. And they're also much more safe. If you're going to hook, it may be the best for your product to hook at the user land. And some products that say they prevent zero-day exploits, other than like stock guard and different things that look at the stack and do canary values on the stack and so forth. That's one technology, but there's also others that actually hook API calls and look for, I'll say, bad stack returns outside of the range of the process. So if you ever have a process or a function being invoked, that when it returns, it's supposed to return to an address that is within the heap, unless it's structured exception handlers and some minute things, it's probably not a good idea that create process just return to the heap because it was called from the heap. So they also hook system calls. This can be easily found in probably any of your leading IDS, IPS vendors' products. You look at the system calls for the registry, for instance, they're almost always hooked. Because if you want to say don't allow people to write to the run key, the way to do that is to intercept that call at the system call level. Then I'm not sure about other OSs, but definitely for Microsoft, there are functions that allow you to register callbacks within the kernel itself. So you can say, upon thread creation, call back my function because I want to know who just created this thread, and so on and so forth. So this is another place where IDS and IPSs can use, and also rootkits themselves. So what's the attack scenario? What's the problem? Well, for a rootkit, usually, like I've mentioned, they gain elevated access through buffer overflows or some other means. The attacker then wants to install a rootkit so that they can come back later. The rootkit will give them elevated privilege access. Also, it will hide their presence. And it could do other things like exfil data. So it could monitor keystrokes and whatnot and exfil that. Here's sort of a brief history of rootkits, where they started, where they are now, and then we'll talk about where they're going with DCOM. So in the beginning, what prompted the need for Tripwire was that these reporting functions, this is a Linux-specific slide, but I guess netstat runs on Windows, obviously. And there's corresponding LS like dir. PS could be like task manager, and so on and so forth. So an easy way to subvert the systems in the old days is just install a Trojan. So take out the PS, put in your own version of PS that hides whatever process you want to hide. And that was the technique. And then, of course, tripwire and some other checksums that look at the file system came along and can detect changes like that. Well, then we see a whole new era of rootkits, which was just to filter data. So they were hooking. These were the hooking rootkits. Originally, I think the first one that I saw for Windows was the NT rootkit by Greg Hoagland. And they would hook the system call table. You can extend this to hook other things. I'll talk about those in the next couple slides. You could hook the system call table. You could hook the interrupt descriptor table. And basically, you filter out the data. So if Task Manager says, give me the list of all the processes by calling ZW query system information, if you're in the execution path, you can filter out the results of that call and hand back to Task Manager some kind of bogus result. Actually, Greg and myself, we teach a training course here at Black Hat where we describe this. We go through how to hook system calls and how to filter data and so on and so forth. One point on the interrupt descriptor table hooking before somebody says that won't work. Older versions of Windows 2000 even, they would call the interrupt int2e to request the assistance of the operating system to grab its attention. Say, now I have stuff for you to do. Please take over and do what I've asked you. Newer versions of Windows have started to use sysenter as of XP and some of the different service packs. What that is it's actually an Intel instruction. And because of that, when you transfer from user mode into kernel mode, you no longer go through the interrupt descriptor table. Now this doesn't work if it's like keystroke, because that actually goes through the interrupt descriptor table still. So what's the control flow in the system? AKA places that someone can hook. If you call create file W, which is the wide character format of create file, you can do this to open a file. If the file already exists, you can get a handle to it by calling create file. So it runs for a while in kernel 32.dll, does its little thing, whatever it may be. Then it calls ntdll. Now ntdll also has a corresponding function to create file W that was in kernel 32, and it's called ntCreateFile. Well, for the most part, it does maybe some checking on the validity of the parameters or whatnot. And then what it does is it puts the system call number. This assumes we're using the int2e technique and not sysenter. But sysenter is similar. It puts the call number of the kernel function, which corresponds to create file, into the register EAX. Then it puts the address of the user mode parameters that were passed to create file W. It puts the address of that user mode stack into EDX. And then it interrupts. It does an int2e, and you'll see there's this line here. So we just did an int2e, and we're going to cross over this boundary between user land and kernel mode. So in the kernel, what it looks like, again, there's the boundary. Everything on this side's in the kernel. There's the interrupt descriptor table, which is an array of the function pointers that is going to handle the interrupt. So if it's an int2e, for instance, in the Windows kernel, it will jump to the KI system service routine. KI system service then will eventually go to the system call. So here an int2e just came in from our create file example, and int2e says, oh, well, the function to handle this is KI system service, and KI system service says, well, I really need to index into the system call table, so that's what it does. And remember, EAX had the system call number, and that's just treated as an index into this array. syscall table is just a big array of function pointers. So you get the address out of this array of the actual function, which is ntCreate file. It's also the same name that ntdll uses, but that's just by hand luck, more or less. It doesn't have to be a one-to-one corresponding. So now you have the address of the function that handles the call, and that's right there, the function. So these places can all be hooked. So I can hook right there, I can hook there, I can hook the interrupt table itself, I can hook all these function pointers, and in 2000, this is like almost 255 function pointers. I can hook any one of those. If I don't like that method, I can just write directly to memory. I can patch the function itself. There's even more advanced ways to hook that I won't get into in this talk, but you're welcome to ask me afterwards and I'll go into it a little bit. So, all that hooking, although very effective, is also becoming easier to spot. And vendors are getting used to this. They're starting to look for this now. So, when I was working for the intrusion prevention company, we wrote code that if you hooked our system call table, or our interrupt descriptor table, or our API stuff, we would see that, and we would report it. So, the next generation of rootkits I call DCOM. And this will use no hooking whatsoever. We'll just understand what the objects are that the kernel reports upon, and we'll modify them directly in memory. So to do this, I wrote a rootkit. It's called FU. It's a play on words with SU command in Unix, and I'm sure it could also have other implications. But it's up on rootkit.com. I go by the handle fuzenop, FUZEN_OP. There's no secret there in who I am. So it will demonstrate all these techniques for you. And the code is, I'm not going to say it's bug-free for sure, but I've tried to do a decent job of commenting it, so if there is a bug, you'll at least understand where it is and what it was doing. So since you have access to kernel memory as a device driver, if you understand it well enough, you can just pound on these structures and still remain a fairly stable system. FU originally was written all in assembly, but that was done for two reasons. One, I didn't want it to get out a lot of the techniques. Since we started teaching the class here at Black Hat, it doesn't lend well to teach a class where you're manipulating structures with assembly. So I changed it and now it's in C. So what can you use DCOM for and where does it not work? Well, this is a list you can obviously read of things that it's good at. So hiding processes, manipulating tokens to elevate the privilege, to manipulate tokens to fake out the Windows event viewer. So basically your chain of evidence in a court file, a court case may be a little bit questionable. I'm not a lawyer, so I'll let you ask Jennifer Granick that question. It'll let you hide ports. The FU rootkit does not hide ports in its current implementation, but this is possible using the same methodology of DCOM. What it's not good for is if you want to hide a file on disk. The reason is that's not so much a structure in the kernel that's persistent in the kernel memory. That's something that's queried by following the inodes of directories and file systems and so on and so forth. So that's not something that's in memory that you can just stomp all over. That's a method where you would still probably want to use hooking to achieve your results. So I think everyone understands the implications of this. One, you sort of have free reign of the system. And I will note here that you could have installed your rootkit as an elevated user and then come back at a later time and use it to bump yourself back up. So regardless of what preventative measures are in place, you know, some of these intrusion prevention systems won't allow you to elevate your token privilege through the normal, you know, Microsoft API calls. Since I'm just writing directly to memory, I don't have to worry about any of the API calls. So it'll defeat a lot of the IDSs and IPSs that are host-based because they rely upon the OS. And it has another implication in forensics to skew the results of that and at least probably lend a little bit of reasonable doubt to the evidence. So how do you go about hiding processes in Windows? I'll also show you how to hide processes in Linux, but it's a little bit different spin at the end of it. So here's just some of the structures that are used by the kernel. There's a linked list of all the processes, and it's called an E-process block. E stands for executive. There's E's and there's K's. K is, I guess, kernel. So there's executive processes, which contain a structure that is an embedded kernel process structure, and so on and so forth. Every process, like this is an individual process, and it's linked to that thread. E thread, again, executive thread. Every process has to have at least one or more threads in the Windows kernel. And then there's this processor control block, which points to the current thread, the next thread to be ran, and the idle thread. And we'll use all this information to eventually find the process we're looking for to hide. So you want to do this DCOM stuff in a relatively reliable fashion and not have to recompile for every single kernel you run under. So you want to gather as much information as you can dynamically. So for one thing, there's this process control block region, which there's books that define what its elements are and how you find it. You could hard code in the address of the processor control block, or you can use the FS register when you're in kernel. When you're in kernel, the FS register is basically leads you to the processor control block, I'll say. So within the processor control block, there's the current thread block. Within the current thread block, there's a link to the current process block. And then the process blocks you saw are all, they're circularly linked. So if you get to the end, you'll end up back at the beginning. And they're doubly linked, so you can go forwards or backwards around the circle. And that's important. So once you get to the E thread, then you get to the, it has a K thread in it. Once you're in the K thread, you can get to the E process block. And from the E process block, you have access to this linked list. And that's what we're going to modify to hide a process. So all we have to do is, you noticed before here, if we wanted to hide this process, the process behind us in the list points to us, and the process in front of us points back to us. So we have to make modifications to both of these E processes. And we can do that basically. The list entry that you saw there contains two elements. It's two pointers, a flink and a blink. So a flink is a forward link, and a blink is obviously a backward link. And if you modify those in the right way, you just tell the processes to point around you. So this is a little animation, no magic. Right here, we've done all the calls, to get the current thread, we've got the current thread, we've got the current process, and in this example, we assume you're trying to hide the current process. But you don't have to assume that. You can walk the list of eProcess blocks until you reach the process you want to hide. So in this case, change the process behind us to point around us to the one in front, and change the one in front to point around us to the one behind us. And we've just totally disconnected ourselves from the list, and the kernel will no longer report that that process exists. And there will be a demo at the end. I'll show you that this is true. So when I originally coded this up, when you start out doing research like this, you find a couple interesting books that are probably the undocumented Windows 2000 secrets or whatever, and they may have hints about some of this, because they'll define what these structures look like, or at least as best as they can through reverse engineering. But you still don't know if your technique will work. Maybe you can now guarantee that you can modify the structure, but there's no guarantee at the end of the day, once you do that, it'll still run. That's sort of the trial and error part. So when I coded this up, I was happily surprised that my process still got scheduled. And the reason is, this is another important lesson to take from this talk, hopefully. Not only do we have no separation of powers between our kernel and third-party drivers, although there is different layers within the Intel architecture that possibly we could leverage to prevent some of this. There's that lesson to take away. And then there's also, if you're an OS vendor or anything else, never report on one element of data and schedule on another, in this case. That's just not good at all. So we'll talk about hiding processes in Linux, because I'm an equal opportunity exploiter. Now I will say that at the end of the talk, or the end of this portion, you'll see that Linux is a little bit different, and this doesn't quite work. But it's not because Linux is some, more advanced OS than Windows. It just happens to be that Linux is so simple, it's sort of lucked into this not working. And I'll talk about that in a moment. So in the Linux kernel, and I'm by no means an expert in Linux, I try to just stay to what I know, which is the Windows. In the Linux kernel, there's a task struct. A task struct is equivalent to an eProcess block in Windows. Within the task struct, there's a linked list. It's a doubly linked list, and it's circular also. That is the previous task and the next task. So by following this list, you'll get all the running processes. But within that task struct, there's an additional element that isn't in the Windows eProcess block, and that's called next run and previous run. And there isn't so much the notion of threads in this context down in the kernel. It's basically based upon processes. So things are scheduled based upon the process. So the task, previous run, next run, point to the task structures of the things to run next, obviously from the name, and the thing that just ran. So if you want to hide the process in Linux, you can modify the previous task and next task, which are just pointers to task structs, but leave the run and the next run, the previous run alone. Otherwise, that's the scheduling mechanism, so you don't want to screw with it. So in memory, in the Linux kernel, this is what the list of processes look like. There's a task array that has pointers to each one of these task structs. And I suppose, possibly, I'm just theorizing here, I haven't tried it, that maybe you could walk this array and get all the tasks, right? So even if people disconnected you here, you would still get the list because it's an array and you can walk an array, you can index it. So you'll see the previous task, next task, linked list, and down here is the previous run, next run. And this is important, this one right here. So this is task struct for process ID 0. Process ID 0 in Linux is the init process. The init process is the very, very first process that's still around when your kernel is up and running. So it has process ID 0, and since it's the very father of all processes, it has no parent. These are pointers to the parent process, child, sibling, etc., etc. So since it has no parent, because it's the init, its parent is null. And we'll use that in a moment. So if we want to hide a process, we can take ourselves out of this list. But I'll talk about why we need to do this. We change the parent of the init process to now point to the hidden task struct. And this is why. So I coded this up in Linux because it's, in Linux it's open source, so you can read what all these structures look like and everything. So it's a lot easier to code up. But the problem was, as soon as I ran it, my process that I was hiding froze. Sometimes the whole system froze, and sometimes it core dumped. So that's not good, and then I was like, why did that happen, So I did a search on Google, and someone else actually had done this same deal before. I'll say up until this point, I did not do this trick. This isn't my trick, this is someone else's. If you do a search on Google under Phantasmorgia or something to that effect, it's like PHA and then Morgia, you'll find that there's a rootkit that does this. I'm not sure if that's the name of the guy who wrote it or the name of the rootkit itself. But he noticed this behavior also, that things froze when you modified these lists. So after I had the problem, then I searched for the cure and came across his work. And he tells why this happens, basically because if you read a good Linux kernel book, you'll see how it'll tell you how things get scheduled to run. And basically in Windows, there's a bunch of queues for the different thread priorities. In Linux, it's not so much done that way. What happens is it runs the list of processes, this linked list, and it calculates a goodness value every time a process is going to be swapped in. So you have to be in that list so that you get a new goodness value. And based upon your goodness value, the kernel will assign jiffies, which are time slots, to your process to run. So if you never get a new goodness value, you never get scheduled. So in this case, Linux, although I believe much by accident, is somewhat immune to this without going through an additional step. The additional step being you have to patch the scheduler so that it knows where to look for your hidden processes so that you still get scheduled time to run. That's possible. Phantasmorgia does it. In this case, you would patch the scheduler to every time you're going to recalculate goodness values. Not only do you have to visit every single task that may be in this linked list, but you also have to visit the parent of the init process and calculate these hidden processes' goodness values. And Phantasmorgia did a very good job of that, so I wasn't going to try to recreate that work. So moving on, what else can we do with direct kernel object manipulation? Well, we can have a lot of fun with tokens. These present their own set of problems, but they seem to be a little more stable than manipulating linked lists and things like that. So within a token in Windows, you have a set of privileges. You may have seen this like the SE debug privilege. you know, you never want to give someone the SE debug privilege, because then they basically can attach a debugger to your processes and single step it or do whatever. You know, debuggers have a lot of power. So there's that privilege, there's the SE shutdown privilege, SE backup privilege, the list goes on. And if you download FU, there's a text file in there called list privileges, so you don't have to worry about it. I'll list out, I've searched all the .h files that I can find from Microsoft, and I'll list all the privileges for you in text, so you can just say, hey, I want to add this privilege to my token, it'll do it. Also within tokens, there are groups, user and group SIDs. And these are really the key. If you can manipulate this, add the system SID or whatnot to your token, then you have all the power of system. It's not as useful, or privileges aren't as useful, because you still are restricted based upon your SIDs in a lot of cases. Also within the token, that's how these reporting mechanisms, like the event viewer and other syslog type programs, determine which process caused the action in many cases. So for instance, if you have detailed process tracking on in Windows, it'll say in the event viewer, you know, Jamie just started regedit 32. And maybe Jamie has no business being in your registry, which is probably the truth. Then you can, forensic consoles and other things, they can use the event viewer to report, hey, this is an anomaly. You have a security posture, you have a security policy within your organization, and this doesn't fall in to the set of actions, you know, you said that the security policy should follow. So then somebody can call you, that person up, and say, hey Jamie, you know, why are you in your registry? This could be very bad. Within a token, it's a little more tricky because there's a static part and there's a variable length part. The static part contains things such as the count of the number of privileges in a token, the count of the number of SIDs, the count of the restricted SIDs, and I won't cover that in this talk. The restricted SIDs are a new thing as of Windows 2000, so they're not totally new, but they're not used a lot in commercial software. Maybe the OS itself from Microsoft uses it, but others don't. And there's also a pointer to where the SIDs are, there's a pointer to where the privileges are, and there's pointers to where the variable length of the token starts. Another important item of interest here is authentication ID. This is called auth ID for some. The event viewer will actually use this D word. It's 4 bytes. It'll use that D word to help identify who the process is running as. So you could say, oh, well, you know, somebody just spawned CMD, and by the way, their auth ID is 03E7. So that's the auth ID for system. So we'll manipulate that in a moment and get some cool results. So within the variable part, since, like I said, we've covered this, privileges, there's a variable number of privileges, so they have to go in the variable length part. Same with users and groups and restricted SIDs. Now there will be a question at the end of this slide, I believe, or the next one. So if you want to manipulate a token, you can't just write at the end of the token, because remember, these are variable length portions, so the static portion of the token and the variable length are contiguous in memory, but you can't just write at the end of the variable length because you have no idea what type of memory you would be stomping on. It could be another token, it could be some kind of space the kernel's using for something different, so it's like the wild, wild west down there and you just can't go there. So an obvious solution to this problem when I first wrote the rootkit using DKOM was I'll allocate memory. Anytime you need to grow something, you just allocate more memory, right? So that's what I did. and I created this new memory up here that had the new tokens and the new privileges, because I had all the room I wanted when I'm allocating. And then remember, in the static portion, there was pointers to the SIDs and pointers to the privileges. So I'm thinking, okay, well, this is cool, because it doesn't have to be contiguous the way the kernel uses it, because it has pointers in the static portion to where these things reside. So they don't have to be right after the static portion of the token. They could be elsewhere. As long as I fix those pointers up to point to my newly allocated memory, everything should work just great. Well, it doesn't quite work that way. What happens is, if you manipulate a token and say you give it system by allocating new memory, well, that works as long as that process never spawns a child process. Once it spawns a child process, all bets are off. You may even blue screen. And I released it this way because I chased it for a while and I couldn't understand what the problem was, and I was sort of out of it now at that point. I wasn't really concerned with it. I'd proven my initial what I wanted to prove, and now I was just sort of writing something for the community. So I released it, and I put in my notes in the source code, here's a caveat: don't start a child process, because it could blue screen. I haven't quite figured out why. Also, the reason to release it and talk about it is so that others contribute. Well, so far, a couple people have contributed bugs, but they haven't really advanced it any yet. So I got an email from someone in England, and they said, hey, this is great, but this token stuff is a little screwy. I'm having some blue screens when I create a child, or DLLs can't be found when there's a child and I try to load DLLs, and so on and so forth. And I was like, yeah, I know, but I said that when I released it. But it's a matter of pride at that point. When somebody calls you on it, especially if it's in a public fashion, you definitely want to go back and fix it. So I said, okay, this is just crap. I shouldn't have released it. I'll go back and I'll spend the time to fix it. So it was about 3 days of soft ice and a lot of coffee. And you run into SEP duplicate token. The P here in this case in the kernel, these are if you have the symbols loaded for your kernel. P usually stands for a private function. In other words, Microsoft is not exporting that from the kernel. It's internal to itself. And what it does is it does some assumptions on where these things lie in memory, as far as static and the variable part, and where the new child token is going to be created, and so on and so forth. So it does some really crazy math. It doesn't use the pointers in the way you would think use the pointers, because child processes inherit the token of their parent for the most part. So you would think, okay, if I'm writing the function that creates the new child token, I'll just go to the parent, look where its SIDs are, because there's a pointer in the static portion that tells me where they are. And I'll go over there, and I already have a count, because it's in the static portion also, and I'll just copy that memory into the child processes token. Well, that's not how it's done. They do some assumptions on the memory layout, and then they do some subtraction. So subtract from where the child is to where the pointer says the SIDs and privileges are, and based upon this distance, we'll know how much memory to copy and where to say the new SIDs and the new privileges are. It's really crazy math, and once I found the line that's doing it, I didn't really care as to learn why they did it that way, because all I need to do is find a fix. So, does anybody have an idea of how you might go about fixing this? Well, you could patch the function, yes, that would work. But that gets, patching live kernels in memory gets a bit hairy. Modifying memory directly as far as structures go gets complicated and a bit dicey at times. So you want a more reliable way to do it, although that would work. Another approach you could take is find room find room within the token to get extra space. And that's what I did. That's like an inline method. So the token doesn't shrink, it doesn't grow, just some of the things within it go away because I decided we don't need them, and that frees up room in our token for the new SIDs or the new privileges. And I'll show you animated slides of this and it'll become a little more obvious. So at the beginning of the variable length portion of the token is a LUID, an attribute structure. Now, a LUID is a locally unique ID, and it's not guaranteed to be the same between reboots. And that's one reason that the FU rootkit has a user land portion and a kernel portion. The user land does the hard stuff like, okay, you want to add SE debug privilege? Well, that's a string, but that string's never found in a token. It corresponds to a number. So it's a lot more efficient to store a number as it is opposed to text. So you can say, give me the LUID of SE shutdown privilege. And the kernel will gladly respond through the API calls and says, oh, well, that's, LUID 13. Then there's an attribute. And that tells you whether the privilege is enabled or disabled. So just because you have a privilege in your token doesn't mean you can use it, because it can be disabled. So like SE debug privilege is usually disabled in all processes unless they're a debugger. Well, disabled privileges sounds like a really good place to look to free up memory. Because if it's disabled, why do I need it anyway? It's not buying me anything. So here on this slide, this is a loose representation, or it's actually fairly accurate, representation of the token in memory. So that's the static portion. In this case, it would say there's 4 privileges in this token. And we don't speak of SIDs right now because we're just adding a privilege, which is all up here. So the static portion would say, hey, well, the privileges begin at this address, and there's 4 of them. The ones in red are the ones that are disabled. The ones in blue are the ones that are enabled. And you'll see in a moment that the added privileges will be in green. So we need to get rid of all the disabled privileges to make room for our new stuff. So we just sort of blast memory, move it around a bit, move around these arrays of privileges. And now we just have the privileges that are enabled. And this gray portion represents all the memory I just freed up to put my new stuff into. So now I have room and I can add my new privileges here. And this could be backup privilege or act as part of the trusted computing-based privilege. This is a similar concept we'll use throughout for adding SIDs and groups too. There's a structure of SID and attributes within this token, and it's an array of SID and attribute structures, and it contains the pointer to the SID, because SIDs are variable length, and it also contains the attribute that describes like the SID may be mandatory in the process, and so on and so forth. I didn't get much into the attributes, I just sort of copied the ones that existed. What I do need to worry about is making a new SID and room for a new SID and attribute structure, and I need to make room for a new SID within the token. So again, play this little trick. Now I've just freed up memory in line within the token, and I can start adding SIDs or SIDs in this case. One thing you want to be careful of when you're doing this is that, say I pass down eight SIDs to my rootkit to add to a token. That's a completely legitimate thing to do. But if I didn't free up enough room to hold all those 8, I need to return an error code because otherwise I'll just start writing over memory through the restricted SIDs and other things. So we want to restore the original SIDs that were there because they were probably there for a reason. So we want to put those back, and those are in yellow or orangish. And the SIDs come at the end of the array of SID and attributes. The actual SIDs themselves are at the end of the array. So we need to make room, that gray portion there is to make room for the new SID and attribute structure, and the gray portion down there we can use for the actual new SID. So all the SID and attribute structures are contiguous, they're an array, and all the SIDs are contiguous. So here comes the new SID and attribute structure, and we update the pointers to point to the new SID. Now, all this is easy to talk about, but there's a lot of pointer arithmetic going on. And it took me a few times to get that all correct. If you want to fake out the Windows Event Viewer, it's sort of a hybrid of two approaches. One, when I first did this, the first thing I did was this auth ID is obviously used if you're the system, but it's obviously used in the event viewer. So all I was doing is a one D-word change to the token to somewhat simulate this running as system. So if the event viewer reported who just ran cmd.exe, it was kludgy, it would almost look like system. So that was the first release. And what happens if you bring up an event in the event viewer, there's like a detailed description window, which is in gray, and above it there's a more higher level description. Well, it turns out I was faking out the detailed description window, but the higher level window really said who this was. So it wasn't a total solution. But I found that if you add a SID, in this case we're just going to add system. So we're going to make everything in the event viewer appear that system did it as opposed to, bad user. So if we add the system LUID, this is hard-coded system LUID. There's about 5 of these I found in a .h file in the Windows DDK, I believe. You can just shove that in there, and you can also make the first SID in the array of SID and attributes, make that the system SID. Now this takes a little bit of different design than our adding SIDs previously, because previously we were adding SIDs to the end of the SID and attributes array. Now we need to add a new first element of the array and keep all the old elements, and then copy in the new first SID and keep all the old SIDs. So it takes it was like a total rework of the add SID functionality. Also, I'll tell you that these auth IDs, other than the 5 or so that are in this .h file, everyone else is assigned a logon ID when you do Control-Alt-Delete and log onto the box. Or I guess if you were coming through the network and your credentials were passed, you would probably get a unique logon ID. Well, that is good and fine, but if you change the auth ID in the token to be the auth ID of someone who doesn't exist or who isn't currently logged in, the system will blue screen. And it's a really cool error because they'll tell you basically something's up with your logon ID. This logon ID cannot be found. So it just barfs all over the place. So this is a mistake I made once or twice. And so you have to almost query every user logged onto the box and then try to find out what their logon ID is if you want to impersonate another user. Else you can just hard code it with a well-known ID. So we'll finish the slides, then we'll go to a demo of this. So really quickly, we're going to talk about how to detect this. I'm not going to go into extreme amount of detail because we run low on time. But the methodology is we can patch the kernel, like I mentioned not doing a moment ago because it's risky. But if you absolutely need a solution to this problem, one, Microsoft can issue a patch where the reporting mechanism and the scheduling mechanism are tightly coupled so that you can't get scheduled if you're not reported. That would be a good thing to do. If you need something like right away, I suppose, you could patch the kernel yourself. But that brings its own set of problems. You know, that's a little bit more high risk. You may not want to do that on your Exchange server and whatnot because some of these services or servers you can't afford to go down. So there's this project that was sponsored by Microsoft Research called Detours. There's the principal authors of that. And basically it was a way to intercept function calls. And if anyone's ever taken a graduate architecture, computer architecture class, or some undergrad classes, they cover, you know, instrumenting code to see exactly how many clock ticks, like maybe create file takes. That's a big thing. There's all kinds of open source projects in Linux that allow you to do this. You instrument code, so you take a snapshot like before create file possibly, and you would take a snapshot after create file, see what the differences in time is, and then you would know exactly how long create file took to I mean, it depends if you get swapped out and different things like that, but you would get a rough estimate. So these guys, or this group, they took and wrote Detours, which is pretty useful. You can also use Detours to write rootkits. It's sort of cool. So if you use Detours, what you do is you overwrite what we'll call a target function, which in this case is swap context, because we want to patch swap context and do a few things before swap context actually runs. So swap context is our target function. A trampoline is just where we store off the bytes we just stomped on. So an unconditional jump usually takes 5 bytes at least. So you want to save off those bytes into your trampoline because you'll eventually need them. And then you have your detour function. So the detour function doesn't call, but it jumps to the trampoline. The trampoline is the target function. The target function therefore returns to the detour, and the detour returns to the source caller. And that's just a little graphic to help you out. So you have no control over who the source was. Somebody in the kernel just called swap context. But what you did, this is swap context, you patched the first 5 or so bytes to jump unconditionally. The numbers may be a little misordered in this example of the usage. To jump unconditionally to your detour. Your detour does some examination on the threads, and based upon that examination, decides whether to really call swap context or just not allow the thread to get scheduled. So what we can do is, if you patch the first 7 bytes of swap context to jump to your detour, then you check the EDI register. The EDI register contains the E-thread block, the address of the E-thread block of the thread that's about to get scheduled. So an ESI is the thread that's getting swapped out. EDI contains the thread getting swapped in. We've already seen that the thread has a link to its corresponding process block. You can follow that link, then make sure that process's neighbors are appropriately linked in the linked list. If they aren't linked, then you should never admit that thread into the scheduler, because it's obviously something's up here, because never should that happen in a regular use case. Did everyone understand that? Any questions? So, question for the audience, why do I say patch the first 7 bytes of swap context? as opposed to 5. Unconditional jumps are 5 bytes long, as long as it's not a far jump. Yeah. Okay, so the gentleman's comment was, instructions on Intel are variable length instructions. So you don't know, 5 bytes may fall in the middle of an instruction, such as a load D word or something, into this register. So you need to preserve function or the actual assembly code, the bytes, and make sure that you're not cutting it in the middle. Because if you cut it in the middle and then you jump to the final 2 bytes of that instruction because you overwrote 5, and you jumped to your detour and then you went through your trampoline, and now you're telling the machine, execute, whatever the last 2 bytes of that 7-byte thing was, the machine's just going to freak out because it may not even be real instructions. Other ways to detect, not prevent. The patching the swap context prevents the thread from getting ran. If you just wanted to detect processes that are hidden using FU or other techniques along those lines, someone from Joanna Rakowska from Poland, she presented at Black Hat Las Vegas 2003, and she talked to this problem of these hidden processes using the FU Rootkit, and she presented a tool she created called KLister. You can now download KLister at rootkit.com. Rootkit.com is no longer, it was always an educational place. It's not for malicious intent, but you can download KLister there, which is a detection mechanism. So we're trying to fan the research into both detection and evasion. So what she does is, there's a list of queues in the kernel where all these threads have to reside. So there's some different types of wait queues, there's different types of priority queues. So if you're in the ready to run state, you're in one of the priority queues, your thread is. If you're blocked waiting on something, you're in one of the wait queues. So if you walk all these queues, you have all the threads on the system. And then you can do the appropriate checks to see, you could see if their process is appropriately linked. If you don't care about that, maybe you just want to list all the processes. You just walk the list of threads looking for their eProcess block. And threads have to be connected to their eProcess block because the eProcess block contains things such as environment variables, the default path, and so on and so forth. So it's needed for future operation of the program. So your threads have to still be connected to the eProcess block. One problem that I see with this is the addresses of these queues are not exported. So you basically have to hard code them in, recompile for every version of the kernel you want to run under, which is, in my opinion, is not a good solution, although I think her work is very, very outstanding. Similar thing to detect hidden processes in Linux, except in this case, detours is not going to be used. It's injectso, which is a library to do roughly the same thing. So since we're almost at the end, we'll hurry up, wrap up here, and then do a demo. So what have I shown? I've shown the next generation of rootkits that I think we'll see a lot of in the future. I just got an email last night. This is the first time this has ever happened, because FU is intentionally written so that it can't just be installed by script kiddie and then used to adulterate your box. It was written so that there's a user land portion, there's a kernel land portion. Anything in user land is always easy to see run. There's also no attempt made whatsoever to hide the rootkit itself. So it's a driver and there's no attempt made to hide it. I tell that you can hide drivers using a similar thing, and if we have time, I'll show you how to do that using the linked list concept, but I don't put that into the FU. It doesn't automatically hide itself. So I got this email saying that they were under attack by the FU virus or something, but they didn't elaborate into what the attack was. So hopefully I can help that person. I think it's probably another virus that's just been renamed. So you're only limited in what you want to do with DCOM by your imagination in many regards. And I would like to see a more tight or more separation, enforced separation between the ODS itself and third-party vendors. Are there any questions before we go to the demo? Okay. Well, so this is the directory with the FU program. msdirectx.sys is the name of the rootkit portion of FU, the in-kernel portion, I would say. Like I said, I make no attempt to hide it. About 8 days after FU went up on rootkit.com, there was a deep threat security advisory workup from Symantec. If you're familiar with that, it was about a 14-page write-up about what FU was, how it worked. The fact that it is a bit insidious because it doesn't call kernel functions, so there's not really a way to stop it. Once it gets in the kernel, you can just pound on memory all day long. But they did say you could detect it by looking for msdirectx.sys. And I named it that, just a little bit of play on words, you know, like Microsoft's DirectX stuff. So first of all, let's open up Task Manager. Everything is sorted in order. System is PID. I'm not sure if everyone can see that, but trust me, it's PID 8 on the Windows 2000 box. And everybody would assume that if you hid system using this process hiding technique and there was any adverse effects, you know, basically if you did it to that process and everything worked, it was probably an okay trick. So FU-process hide 8. So -PH is process hide and 8 is the PID. And everyone can still see system up there, sort of highlighting grayish. It's gone. Thank you. The box will continue to run just fine. Now I'm not going to run KLister, but trust me, KLister can see that. Although I think I have a way to get by KLister now, but I'm not sure if I'm going to release that or not. I'm not really into the whole arms race thing. So PID 1880 is this process right here. Different command shell. We can get rid of this now. And if I start up regedit, everyone familiar with regedit 32 will know that the security tab is grayed out because I don't have access to that. I'm administrator at this point. I can take access to it, but I don't have access to it by default. So that's where the SAM database is stored. All your hash passwords and so forth is within that security key. So that would be bad if you elevated your privilege and then you could look at that key. So if we go back to, oh, by the way, this tool is Process Explorer from sysinternals. It's pretty good about showing the different processes that are running and the tokens and privileges associated with the process. So you see there's a whole list of privileges down in this window. However, most of them are disabled by default. There's usually like 17 down there, and only about 4 or 5 are actually enabled. And that's what we're taking advantage of. That's where we're going to get all our free space, by getting rid of those disabled tokens, or privileges. And then up here in this window is the list of users. And you'll notice there's no systems group in this token. There's just administrators, users, debug user, blah, blah, blah. So if we say FUPSS, which is privilege set SID, and we give it a process ID of, what was it, 1880? 1880. And we say give it system group. You see the green bar because FU just started up. Oh, that's not good. We did have this happen once in class. Yeah. Okay, well, the CPU utilization spiked for some reason, so I'm not sure exactly the cause of that. But we're probably not going to see it take effect. Yeah, it hasn't modified the token yet. For that, I'd have to reboot and do it again. Which kind of sucks, but live demos always have a hiccup in them. Since that process died, I may have recovered to a degree. No, it's still spiked. Well, although it says the process died, it's still running, so I'll have to reboot. My email and so forth is in the slides if you want to see it. Send me an email. I'm happy to answer questions. Just mention that you were at this show or took the class or whatever, and I'll be sure to give you my attention. And if anybody wants to stick around and see this work, as soon as I reboot, you'll see it work. There's a new version of FU, and that may be the problem. So if somebody wants to read the source code and contribute a patch. Yeah.
If a privilege is not explicitly enabled or disabled, what is the default option? Disabled or enabled?
Disabled. Yeah, it has to be explicitly said that this is enabled. Yeah.
You mentioned that checking hooking is pretty easy. How do we go about doing that? Down looking at syscall.
Right. Well, you have to have. I can't get into everything in that arena because the techniques I developed. Yeah. The question was, how do you detect hooking if I claim that it's easy to detect? And the answer is that I can't get into all the specifics of it because when I was doing that work, I was under non-disclosure agreements and so forth. But if you have, I will tell you, obviously, you can examine the system call table, right? And if you have an understanding of what it should look like, you can then determine that it's been hooked. In other words, the system call table, every single function in that system call table resides within NTOS kernel.exe. So if it's well, I won't say any more about that, but it's there. Any other questions? Yeah, we had go ahead. We had a problem in the class with another gentleman running the FU rootkit. What it does is it runs around the list really quick to to find the process you're trying to hide. And it appeared that that didn't always terminate, because I tried to take a snapshot of where I started in the list and then run around. So if somebody gave me bad parameters of a PID that doesn't exist, if you didn't say where you started from, you would just run around that loop really tight. And that's bad. Obviously, you spiked the CPU, which is what happened. So there must be some problem in my termination routine. Also, when you saw the blue screen when it went down, the reason for that is because the kernel's going down, because I said shut down, remember? The kernel's going down, it's cleaning up these structures, it's freeing memory, but you know, there's still FU like trying as hard as it can to get scheduling, and it's going to touch something that's been torn down. Because it doesn't get a mutex. Typically, if you're writing something to list processes, and you're in the kernel or you are the kernel, you get a mutex to that list, and then you get exclusive access to it. You walk it, do whatever you want, and that way you can guarantee nobody's adding a process to the list while you're there walking it. I don't get that mutex. So I can get swapped out, somebody else can modify the list, and then I get swapped in. Maybe I've already saved off some of those pointers, and so I'm making assumptions about memory that's no longer there. If you want to do this in a completely stable way, you have to get the mutex. But the mutex isn't exported by the kernel. So what? EX resource light, right? Oh, to disable the interrupts? Yeah, there would be that, possibly. And also, I think you could possibly find the mutex. Like maybe within XP, the mutex is at offset 20 from the process, linked list process head. So you could just sort of hardcode and make some assumptions in that case. So, then 52. So first of all, we'll start regedit. Excuse me? Oh, yeah, thanks. Okay. So I just started regedit 32. Again, I don't have system privilege, so that's grayed out. Now I'll close this process down. I'll run fu-pss. It was 11:52, I believe, but I need to make sure of that. Yeah, 11:52 is my CMD process. And if this doesn't work, we're just going to call it quits and go to lunch. So we'll go add the system. So now system token hopefully has been added to this process, and we'll restart regedit 32. And if it all worked, then we should not have a grayed out field. So there we go. Now we can get down to the security SAM database, blah, 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 because we're the system, although we're logged in as administrator in this case. So that's the end. Thanks for your attention.